Hello everyone, in this video we're going to be talking about nucleophiles and electrophiles. It's extremely important to understand what a nucleophile and electrophile is. Not only that, it's also important to be able to identify your electrophilic and nucleophilic sites on a given compound. So let's start out with a nucleophile. As the name specify, nucleophile is going to be a nucleus lover, or another way of saying a positive charge lover, because remember nucleus has a bunch of protons on it and they have the positive charge on it. So in order to have an affinity for the positive charge, what must a particular chemical have? Well, it must have a bunch of electrons on it. Or another way of saying, any chemical that has an electron-rich center can act as your nucleophile. And we're talking about the loose bases and the bronzoluric bases. They also have a bunch of electrons on them, and they could also act as your nucleophiles. So let me take a few examples of compounds or a few different types of compounds that could act as your nucleophile. The first example is going to be lone pairs. I can have neutral compounds, and those neutral compounds containing an atom that has lone pairs, like in this case water. In water we got oxygen with a lone pair of electrons, so that's going to be a nucleophile. It may not be the strong nucleophile, but it still can act as a nucleophile because you got a lone pairs on the oxygen atom. I can talk about any sort of alcohol, CH3OH. So again, in CH3OH, we have the lone pairs on this oxygen, and since we have a lone pair on this oxygen, they can be donated. As a result, they could be acting as your nucleophile. I can have ammonia or even amines. In ammonia, nitrogen having a negative lone pair of electrons, so that can also act as a nucleophile. But not just only those, you can also have the negatively charged species. They can also act as a nucleophile. If I take an example of maybe OH minus, so hydroxide, remember hydroxide is also a base, but it can also act as a nucleophile because now it's got a bunch of electrons on it. Now if I want to compare with water, like the water and hydroxide, they're both going to be acting as a nucleophile, but who's going to be a better nucleophile in this particular case? Well, obviously your hydroxide because you have more lone pairs on that oxygen in case of hydroxide than in case of water, and obviously as a result that gives you the negative charge as well on that hydroxide. I can talk about maybe even methoxide or any sort of alkoxide where you don't it's coming from the alcohol but you don't really have the hydrogen anymore, so you have removed the hydrogen by doing an acid base reaction, and now you got an excessive electron pairs on the oxygen. So that's going to be your examples of nucleophiles. In addition to that, you can also have pi bonds that can act as your nucleophiles. So pi bonds are electron rich centers. You can have a double bond or you can have a triple bond, and as a result, having a bunch of electrons on them, they could be acting as your nucleophiles because you have those unhybridized p orbitals in there, and they are the one that's carrying those electrons in those particular cases. In addition to that, the partial negative center in a given compound can act as your nucleophile. So this is probably going to be the most difficult and the most important probably to be able to identify. You can easily identify a nucleophile based on the lone pairs in a given compound and even based on the pi bond. But when you're given actually a compound, how can you figure out where your electrophile going to be and where your nucleophile going to be? So your nucleophile is going to be a partial negative center. So I can talk about something like, let's say I got this CH3 and a lithium bond. Now, what do I know about this carbon and lithium bond? I know lithium is a metal and carbon is a nonmetal. So as a result, this bond is more likely going to be behaving as an ionic compound, where lithium is more prone to lose electrons. So it's going to be having a you can even say a full positive charge, or let's say a partial positive charge, since it hasn't lost electrons completely. It's a partial positive charge here, and this carbon's going to have a partial negative charge. And you may see even in some books writing as a full negative charge, because as soon as it's put in the solution, this bond breaks where carbon gets a full negative charge. So then in that particular case, we can clearly see that this carbon having the negative charge or a partial negative charge is going to be your nucleophilic center. or acting as an nucleophile. What's the other example I can have? What about having um, a bond, something like this? Well, we know already that oxygen does act as a nucleophile, but what else we can tell about it? The carbon and oxygen bond is going to be a polar, and as a result, this carbon is going to be getting a partial positive charge, and this oxygen is going to be getting a partial negative charge. So between the carbon and oxygen only, I didn't really talk about the hydrogen here. Between the carbon and oxygen only, who's going to be your nucleophilic center there? But remember, carbon being less electronegative gets the partial positive, oxygen being more electronegative gets a partial negative. So as a result, oxygen getting the partial negative charge, this is going to be your nucleophilic center or your nucleophile in this particular case. So depending on who the carbon is really bonded to, it can act actually as an electrophile or a nucleophile. So it's all about the electronegativity difference. Okay, let's talk about the electrophile. As the name specify, electrophile is going to be your electron loving species. So in order for a chemical to have an affinity for the electrons, it must have a positive charge or it must have an incomplete octet in there. And loose acids and even like your H plus, that's going to be acting as an electrophile. Now you don't really call H plus as an electrophile for the most part, but it still can accept a pair of electron, or it still can have an affinity for the electron pair. So for the most part, the H plus is usually called an acid, but acids are indeed going to be your electrophiles. So let me give you a few examples where you have these electrophiles. I can have carbocations. So carbocations, I'm going to have a carbon with a positive charge. So still in a cation, but now we're going to have a carbon with a positive charge. So in this particular case, you have a carbon with a empty p orbital, you can say, and you can also say this carbon is going to be an sp2 hybrid, and it doesn't really have the octet completed either. Um, Having the positive charge here, this particular chemical can easily accept a pair of electrons. So as a result, this site is going to be your electrophilic site. What about a partial positive charge in a given compound? And that goes back to the other example that we were doing earlier. So suppose I have something like this, CH3Cl. Now, what do I know about this bond between the carbon and chlorine? Chlorine is going to be more electronegative than the carbon. As a result, chlorine is going to get a partial negative charge and carbon is going to get a partial positive charge. So who is going to be your electrophilic center there? So remember, your electrophilic center or electrophile is going to be the atom in a given compound that either has a full positive charge or even a partial positive charge. So in this particular case, carbon is the one that's getting the partial positive charge, so that's going to be acting as your electrophile. And then, I can take a maybe other example where I have suppose a double bond with the oxygen, so now that's like a ketone here. And in this particular carbonyl or a ketone, I know oxygen is more electronegative. As a result, this oxygen is going to be getting a partial negative charge, and this carbon that's bonded with the oxygen is going to be getting a partial positive charge. So since carbon is getting the partial positive charge here, that particular carbon is going to be acting as your electrophile. So carbon could act as an electrophile or an nucleophile depending on who it's really bonded with. Like in the previous case, when it was bonded with the lithium, it acted as your nucleophile because it had either a partial negative charge or when it's dissolved in the solution, it would have a full negative charge on it. So then what about something that has an incomplete octet? Well, we did talk about the carbocations having the incomplete octet, but that does have a positive charge. Now you can have neutral species that actually have an incomplete octet and they have maybe only 6 electrons and they can accept a pair of electrons to make a total of their octet completed, and those are going to be also acting as an electrophile. And those are actually going to be typically the examples of loose acids. For example, having BH3 or BF3, or even something like AlCl3, or even AlBr3, or FeBr3. So all these guys, all those metal cations, they have the potential to act as your Lewis acids, and Lewis acids can act as your electrophiles as well. And I'll go ahead and write down the H plus as well. We don't really call H plus for the most part as an electrophile because it just have a special name and is just usually called an acid. But it does falls in the same category. It is able to accept a pair of electrons, so it is going to be indeed also an electrophile, but you just have a special name for it and you just call it an acid. Okay, let's look at some of these examples I got here. So we got to figure out your electrophilic and your nucleophilic center there. So remember, your electrophilic centers are going to have either a positive charge or a partial positive charge. So I'll go ahead and write down here a positive or a partial positive, and your nucleophilic center is going to have a negative charge or a partial negative charge, or maybe have a bunch of electrons on them. So I'll write down electrophilic center as EC, and I'll write down your nucleophilic center as NC. So that way I'm not writing the full words in these compounds here. So let's look at your first compound. I got an alcohol here, and I know the bond between the carbon and oxygen is going to be polar, where carbon is going to be getting a partial positive charge and oxygen is going to be getting a partial negative charge. And what about this hydrogen? Well, hydrogen is also less electronegative than the oxygen, so as a result, this hydrogen will also get a partial positive charge. So, well, we have two partial positive centers, so this is going to be your electrophilic center. The oxygen having a partial negative charge is going to be your nucleophilic center. What about this hydrogen? Well, it is indeed going to have a partial positive charge, so it is indeed an electrophilic center, but it does have a special name. We're just going to be calling that as an acid instead of calling it an electrophile. Then what about this next one here on the right side? I got oxygen carbon double bond. So it's in a ketone functional group. So remember, this carbon is going to be partial positive and this oxygen is going to be partial negative. So I know this partial positive is going to be your electrophilic center, and then your oxygen is going to be the nucleophilic center there. What about this next one here? We got a carbon-chlorine bond. So chlorine is indeed more electronegative, so it's going to have a partial negative charge. Carbon is going to have a partial positive charge. So chlorine could act as your nucleophilic center, and then your carbon could act as your electrophilic center. Chlorine is also a really good leaving group. So instead of acting as a nucleophilic center right away, it usually leaves, but that doesn't take away the fact that it does have a bunch of electrons and it could possibly act as a nucleophilic center. What about the CO2? I didn't really draw out the structure, so make sure you go ahead and draw out the structure of CO2. And if you recall, CO2 is a linear molecule where you got one carbon bonded with two oxygens. And remember, overall carbon dioxide is nonpolar. Even though the overall polarity is nonpolar for the carbon dioxide, the bonds in the carbon dioxide are polar because oxygen is going to be more electronegative. So both of those oxygens are going to be getting a partial negative charge, and this carbon is going to be your partial positive charge. So as a result, carbon would be acting as your electrophilic center, and very likely if you want to say these oxygen could act as your nucleophilic center. And there. Okay, what about this next one? Well, that's a similar one I did earlier. So we got a carbon lithium bond. And like I said, if once you put them in the solution, this kind of becomes an ionic compound where this carbon is going to get a full negative charge once it's separated. So let me just go and write down as a partial negative first and a partial positive on the lithium. But once it breaks up and once it dissolves in the solution, this is how you're going to be writing it. Sometimes you can write the lithium as a full positive charge and carbon with a full negative charge. But in either case, this carbon is going to be your nucleophilic center, and this lithium, well, technically, lithium doesn't really act as your electrophile. That's because if you go back to the compounds or the bases of lithium, like lithium hydroxide, that's a strong base, and the strong base cations doesn't really act as acids anymore. So this doesn't really act as an acid, but it does have a positive charge that you want to keep in mind. What about this next one here? Well, we got a pi bond there, so obviously that's going to be acting as your nucleophilic center or acting as a nucleophile there. I got these two equations there, and the reason I have two equations there, your in terms of the mechanisms when you're doing your organic synthesis mechanisms, about 90 or I even say 95% of your mechanisms going to start out with your nucleophile, electrophile, or your acid and base. And they are similar. Your acid and base or nucleophile electrophiles, their arrows are similar. So it's extremely important when you're looking at your chemicals to be able to understand where your nucleophile is and where your electrophile is. And believe it or not, a lot of times students get into the second semester organics chemistry and they don't even know what the difference between a nucleophile and electrophile is. This is something that you would learn somewhere in the middle of organic 1 or maybe in the beginning of organic 1 depending on the type of book you're using. So in this first example, I can clearly see I got an OH with a bunch of electrons on it, so that could either act as a nucleophile or it could act as a base. But when I look at my other compound, I got a carbon-chlorine bond, so I know this carbon is going to be a partial positive charge and this chlorine is going to be a partial negative charge. So how the arrow is going to look like, your arrow always starts from your electron rich side and it goes to an electron deficient side. So in this case, your arrow is going to start at the OH electrons and it's going to go on to this carbon. Okay, and then remember this carbon already has 4 bonds. Obviously, it does have 2 other hydrogens on it that I'm not really showing there, and I'm not going to show because it's just going to make it too crowded. But when you're doing so, you don't want to make it pentavalent. That's going to be exceeding the octet of the carbon. So in order to not exceed the octet of this carbon, what has to happen? Something must break away. And in this case, having a polar carbon chlorine bond, this bond is going to break away and this bond is going to go on to the chlorine as an extra lone pairs now. Okay, so at the end of the day, I would have a chemical that's going to look like this. I made a new bond, okay, so I'm going to show that with a yellow color. I made this new bond here that's going to be between that carbon and that OH. And then the chloride has left, where chloride is going to have now 4 pairs of electrons with a negative charge. Because remember, it already has 3 lone pairs on the chlorine, but now all of a sudden it's going to take away 1 more electron pair when you break the bond, and now it's going to have 4 lone pairs of electrons. Remember, you always have to conserve your charges. If your reactant has a -1 charge as your starting point, your product must have a -1 charge. This OH in this particular case is going to be acting as your nucleophile. And this particular carbon right there is going to be acting as your electrophile. So I'm going to write that down here. Okay, so that's this reaction. Let's look at this next one here. So when I'm looking at this next one here, I still have the same type of second chemical. I still get the OH minus. That means it's going to be either acting as a nucleophile or a base. That depends on what other chemical you have in there. When I'm looking at my other chemical, we have a carbon oxygen bond, and you could say that this carbon oxygen bond is indeed going to be polar, and where this carbon is going to be getting a partial positive charge and this oxygen is going to be getting a partial negative charge. But then remember, this hydrogen oxygen bond is also polar, where this hydrogen is going to be getting a partial positive charge as well. um, So that it does have two sites to attack for this nucleophile coming in. It could either attack on that partial positive carbon or it can grab that partial positive hydrogen. Turns out it's not going to grab the partial positive, it's not going to attack the partial positive carbon because the OH is a bad leaving group and we can't really have 5 bonds on that particular carbon. So you will learn about leaving groups later on, but instead of attacking the carbon, it's going to go ahead and actually grab the proton. So since this grabs the proton like this, and then obviously you can't really have 2 bonds on the hydrogen, so what's going to happen? This bond right here is going to break and it's going to go on to the oxygen like this. And as a result, I'm going to get a oxygen now with a extra lone pair of electrons, so it's got a negative charge and getting water in there. So what particular type of reaction is that? So your how it attacked doesn't really change. Like you still have the electron-rich center attacking an electron-poor center, however, in this particular case, it grabbed the proton, and since it grabbed the proton, we usually call that an acid-base reaction. In this particular case, this OH is going to be acting as a base, and this hydrogen is going to be acting as your acid. But your overall scenario still stayed the same. Your arrow started from the base and went to the acid, and in the previous example, your arrow started from the nucleophile and it pointed toward the electrophile. So whether you're doing an acid-base reaction or a nucleophile electrophile reaction, your mechanism more or less is going to be very similar to one another. It's just a matter of like whether you're going to want to call it electrophile, nucleophile, or you want to call it an acid and base. All right, if you have any questions on any of those concepts, feel free to leave any comments in the section below.